Hello everyone, my name is Suhail and my advisor is Professor Kelim Bilta from the Boston University Robotics Lab. Today I will be presenting the work we submitted to the CDC 2021 titled Neural Network Based Control for Multi-Agent Systems from Spatio-Temporal Specifications. This work was done in collaboration with Nosheen Mahdibar from Motional and Professor Ezio Bertucci from the Technical University of Vienna. In a nutshell, we propose a framework for solving control synthesis problems for multi-agent networked systems required to satisfy spatio-temporal specifications. So multi-agent systems are used as models in many applications, ranging from robotics to power networks, smart cities, and synthetic biology. An interesting class of multi-agent systems is wireless ad hoc networks. It's basically a team of agents connected wirelessly. The agents are usually doing some tasks, such as monitoring the environment or doing some navigation tasks and so on. Each agent can be equipped with task-specific equipment, as well as some wireless communication device, such as radio transceivers. Each agent can move independently in any direction and changes its connection links to other agents, and since the name ad hoc networks. Planning and controlling the motions of such systems is a difficult problem, which have received a lot of attention in recent years. One of the main challenges is specifying the motions and capturing their spatial properties. Let's have a look at some of the literature on specifying properties for such systems. So existing approaches include consensus algorithms in which the specification is to reach a desired global state. This could be the minimum or the maximum inter-robot separation, some specified centroids or heading alignment. And the second approach is abstractions, in which a team is parameterized by a set of features, such as the mean, variance, or orientation. For specifying properties, there is also formal languages which have been widely accepted as a way to specify spatial and temporal requirements for dynamical systems. So let's have a look at the temporal logics and also the spatial-temporal logic, signal-temporal logic. It's a formal language designed for specifying temporal properties of continuous time real-valued signals. And recently, temporal logics have emerged as a formal way to specify both spatial and temporal requirements for spatially distributed systems. Examples include SPATO, SSTL, STRL, SISTL, STL, and the common theme among all of these logics is that they use signal temporal logic to present the temporal aspect of the system, and they use spatial logic, which captures the spatial aspects of the system. For example, SPATO uses STL for the temporal part and which is a tree superposition spatial logic to specify the spatial aspects of the system, and so on. There are other logics that use operators, such as STRL, which is what we will focus on today. STRL basically uses STL to specify the temporal aspects of the signal, and it also uses spatial modalities to capture the spatial aspects of the system. There are also a lot of other logics and corresponding spatio-temporal logics that build upon this. And we'll focus on STRL in this work. The main contributions can be summarized as follows. So first, we propose novel, smooth, quantitative semantics for STRL. Second, we propose a hybrid optimization approach for solving the control synthesis problem for multi-agent network systems from spatio-temporal specifications, given as STRL formula. While hybrid algorithms have been used before, to the best of our knowledge, this is the first time they have been employed for control synthesis. Last, we provide fast recurrent neural network-based real-time controllers. So next I'll be defining the system. Consider a team of n robotic agents. Each agent has a state, which can be constant attributes, such as the type of the agent. And we have some variable attributes, which are, for example, the position of the robot, dynamics. In this example, we have very simple dynamics here. We define some connectivity conditions among the agents. For example, agents can be connected if they are within a communication range. We model the time-dependent inter-agent connectivity using undirected connection graph. At each time, we have one connection graph, which consists of the agents and the connections between them. We define a route as path on a connection graph. For example, here we have agent 3. A route from agent 3 would be 3, 6, 5, 2, for example. And then we use the notation routes, lambda, k, and l to denote the routes starting at L. Let's have a look at spatio-temporal reach and escape logic. STRL is a logic language capable of describing complex spatio-temporal properties of systems. STREL has formulas that are formed recursively using atomic propositions, linear predicates, which can capture the variable attributes, logical operators such as not, or, and then there are some temporal operators such as always and eventually. Then there are spatial operators. Some of you might be familiar with the temporal operators because there are lots of works on that, but for the spatial operators, we'll have a look at an example. We have two spatial operators. The first one is reach, the second one is escape. And from these operators, we can derive other operators as well. So STREL has qualitative semantics, which define the satisfaction of an STREL formula. And we say that the state of the system at a given time satisfies a given formula. So in this example, we're looking at the system that we just saw before. In this case, we have 8 agents. The red ones are end device, the black ones are routers, the blue ones are coordinators. And we have a formula here. This is an STREL formula that says a router reaches an end device within one hop, with a maximum of one hop, where hop is just basically one jump. So at agent number 2, we can see that it reaches a device, it reaches an end device or a red agent within one jump, one hop. On the other hand, agent 6, since it's not a router, it does not satisfy the formula phi1. STREL also is equipped with quantitative semantics, which is represented by the robustness metric. It enables evaluating the satisfaction of a formula. So instead of saying the formula is satisfied or not satisfied, we can say a formula is satisfied by this much. And for this robustness, positive values mean satisfaction and negative values mean violation of the formula. We'll start by discussing the limitations of the original semantic we just saw. First is robustness does not depend on the distance between agents. For example, the formula end device reach a router within 2 jumps will have the same robustness score for agent 3, agent 6, and agent 5. Even though agent 5 reaches the router within 1 step, agent 6 reaches it within 2 steps. But if we have, for example, Euclidean distance and we want the agents to be as close as possible to the router, we need to capture the distance and the robustness. The second is that there is no notion of spatial count. Why is this important? Imagine there's a scenario where you want to, for example, your agents to surround the target, and you want to maximize the number of agents that surround this target. So you will need to have robustness of agent 2 higher than the robustness of agent 4. The robustness is defined on the level of agents. So each agent satisfies or violates the formula. But if we want to talk about the system in general, there is no notion of robustness for the whole system. Finally, the robustness metric is not smooth due to the existence of the min and max operators. We address the limitations in the following way. So you can see here an example of the novel semantics. We added a few functions, sigma routes. We added sigma distance, and we added also sigma agent. Sigma distance varies by distance between agents. So for the formula that we saw in the previous slide, agent 3, 5, and 6 will not have the same robustness. In fact, agent 6 will have higher robustness. It has more routes that satisfy the formula. In the same way, sigma routes accounts for how many routes are satisfy the formula. So now agent number 2 will have higher robustness than agent number 4. We have sigma agent, which captures the robustness for the team, like how many agents satisfy the formula. And we also approximate the min and max operators with smooth versions of these operators. Next, let's introduce the control problem. Now we want to find the control sequence robustness function and minimizes the cost function. And we have some constraints, which is the dynamics of the system and the control bounds. So let's consider the same system that we presented in the previous slides. And now let's talk about choosing the optimization algorithm. Consider the same system, and now let's consider the following specifications. So the specifications, what it says here is that always between time 0 and time 13, the distance between any 2 agents should be greater than 0.15. This basically guarantees that the agents do not collide. And the second, and between time 3 and time 13, each end device, which is here in red color, should reach a router within a distance of no more than 2. And this is what you can see here, that the red agents always are close to a black agent or a router. And finally, the distance between each agent, each end device, each red agent, to the origin of the coordinates here is less than or equal to 0.4, which is the circle here. So we solved this problem with 1,200 random initializations from this box, and this box from the boxes here and here. And what we saw is that the gradient-based method, sequential quadratic program, had a low success rate below 50%. They converge to a local minima, and such local minimas can have negative robustness, and that's why we have like a low success rate. Particle summarization, which is a heuristic algorithm, achieved higher success, but the robustness was a little bit lower. And when we combine PSO and SQP, which is like heuristic plus a gradient-based algorithm, we get high success rate, which is very good. And then we also get high robustness. However, this comes in a small cost of time. And that brings us to the next topic, which is optimization algorithm do not meet the requirements for real-time control. As you can see here, the times are very high. So we proposed learning controllers using the recurrent neural network that are given by this formula, with an objective to minimize the difference between the control and the predicted control. And what you can see here is an example of 3 executions from the same point, and the dashed lines are the trajectories generated by using optimization, and the connected lines are those generated using the recurrent neural network. So you can see here that the success rate is comparable. The robustness is a little bit lower for the recurrent neural networks. However, the time meets the real-time requirements for control. To summarize, we proposed a framework for solving control synthesis problems for multi-agent network systems from spatio-temporal specifications. For future work directions, there are multiple interesting directions that this research will go to, which are using reinforcement learning for online learning instead of learning from offline generated samples. And the second is addressing the scalability to large teams of agents, and also to provide safety guarantees using control barrier functions, and so on. With that, I end my presentation. Thank you all for listening, and I'll be happy to answer your questions.